Hey guys, today we're going to talk about piecewise defined functions. A piecewise function is one where the function rule varies based on the input interval. That means that I might have several different functions happening at one time on the graph, but I just split up the x interval where each function takes place, and that guides what we're going to see. We've already seen several of these in examples, but basically the biggest thing you need to know is that no endpoint can be used in two different domains. Otherwise, the function wouldn't pass the vertical line test and it wouldn't be a function at all. And I think this will become more apparent once we start to look at these and graph them. So as you can see, in my definition, I have that f of x is defined here as being multiple rules. I have it up to rule n, but it's usually only 2 or 3 pieces. And each rule comes with the domain where it's specified. And so when I come down here to my examples, the first thing I'm going to do is I'm going to evaluate the function for different function values. The purpose of doing this is just to let you see how the intervals determine the value of a function at any given point. So for the first one, we have let f of x equal 7x plus 3 if x is less than 0. And then let f of x equals 7x plus 6 if x is greater than or equal to 0. So I'm going to evaluate these different function values. First, we're going to find the value of f of x when f is equal to -1. So I write down f of -1, and I'm going to write down the rule that applies when x is equal to -1. In this case, we see that if x is less than 0, then our function rule is 7x plus 3. So I'm going to go ahead and use 7x plus 3, but instead of x, I'll put my input of -1. Plus 3 comes out to -7 plus 3, which is -4. So the value of f of x at the input of -1 is -4. Scooch these on down a little bit, and then we will take a look at f of 0. Now, according to our function rule, notice it says if x is less than 0, then our function rule is 7x plus 3. But in this case, we don't have less than 0. We're going to have that x is less than or greater than or equal to 0. This is where our function rule or function is going to be evaluated, because in this case, 0 is in the second interval. So my function rule there is going to be 7 times x plus 6, but instead of x, I'm going to substitute 0, which is my function value or my function input. 7 times 0 is 0, plus 6 is 6. So f of 0 is equal to 6. Should have written that for the previous example, but here we go. Last, I'm going to evaluate f when the input is 4. And we're also going to use the 7x plus 6 again, because 4 is greater than or equal to 0. It's the greater than part. So I'm going to do 7 times 4 plus 6. 7 times 4 is 28, plus 6 is 34. That means that f of 4 is equal to 34. Right? On the other hand, I can take a look here at my second function, and this function is defined over 3 different pieces. Our first piece is x to the power of 3 plus 1 if the input is less than 0. If the function's value is 4 for any input between 0 and 3, including those endpoints, because I have 0 less than or equal to x less than or equal to 3. And then I have, if x is greater than 3, my rule is 3x plus 1. So let's go ahead and see what that means in terms of evaluating these functions. For this function, f of -1 is going to put us in our first interval where x is less than 0. So that means that my function rule is x to the power of 3 plus 1. But my x that I'm going to be evaluating is -1. So -1 times -1 times -1 is -1, plus 1 is 0. So f of -1 is equal to 0. For f of 0, that means an input of 0. And I go down to my second rule here, because my input is between 0 and 3, but equal to 0. So f of x is equal to 4 when 0 is less than x, which is less than 3. So we just have f of 0 equals 4. We don't have to evaluate anything else. We just know that it's 4 for any input in that range. And last but not least, we are going to find the function value when we have an input of 4. That pops us down to our last function rule, 3x plus 1. So 3 times 4 plus 1, because 4 is greater than 3, so it's in our last domain. So 3 times 4 is 12, plus 1 is 13. So that gives us f of 4 is equal to 13. All right, so now we're going to apply this to graphing. And I think when you see these graphs, this is the part where it's going to look familiar. So down here, our next example is going to be to write a formula for the piecewise functions that are graphed below. So these are all constant functions. You can tell because they're flat and they have a 0 slope, which means that all we're looking at is our y coordinate. Because you would think if we have y equals mx plus b to define these lines, these all have 0 slope. So you just get y equals b. So we're just looking here. This function, this first piece, it has a y-intercept of 2, and it means the function value is 2 when x is between -6 and -1. Notice that I put less than or equal to because here I have completed circles here. So it's a closed circle, so I have an or equal to relationship. For this puppy here, hold on, let me get this guy going in a different color. For this piece, my b is equal to -2, or my equation is y equals -2. Whereas the first one was y equals just 2. Positive 2. This y equals -2, it takes place when x is greater than -1 and less than 2 or equal to. I use just less than for this part here because it's an open circle. And then I use less than or equal to because the second point is a closed circle. Let me scooch this over to the side so you can actually see what I wrote here. All right, so I only have a less than or equal to for the second part because it has a closed circle. And then my last piece of this function, which is a 3-piece function, is here. And I can see that in this case, y is equal to -4. And this is happening when x is greater than 2 and less than or equal to 4. So we can define our function using these 3 intervals. F of x is equal to our 3 functions, 2, -2, and 4. And we're going to record the interval over which this is true. So first we have -6 less than or equal to x less than or equal to -1. Both of those are closed circles on the line, and so I use or equal to in my inequality or in my function. My next one, f of x is equal to -2. That's when x is between -1 and 2. And I only have a less than symbol here and a less than or equal to here because of the closed circle and the open circle. And then finally, if x is between 2 and 4, not including 2, but including 4, then I have y equals -4. And this is the function rule that matches up with this graph. Now, it's not always lines. We can have a function like we saw before that has a cubic or any kind of parent graph or parent function you can think of. We can write a function that matches that graph. So here we have f of x equal to two different pieces. Here in this first piece, this is a linear relationship. I have an arrowhead on my line, which means that when x is less than or equal to 3, no, when x is less than or equal to 0, I have this graph of y equals 3. For this second piece of the graph, here where it's a parabola, we're going to have to think about the parent function for a parabola, which is x squared. And it's not shifted at all because my vertex is here at 0 and 1, 1 is on the graph, and so is over 2 up 4. All right, so I know that this is just my regular parent function of y equals x squared. And I'm going to write my two functions here. My first function is y equals 3, so I'm just going to write f of x equals 3. And that happens if x is less than or equal to 0. Again, I know that it's or equal to because I have a closed circle on my 3. I'm sorry, on my point 0, comma 3. Right, and then for the second part, I have y is equal to x squared, and that happens when x is greater than 0. I don't use or equal to because I have an open circle here at the origin. Right, so this is going to require that you know your parent functions, and so I highly recommend that you keep those handy in your notes so that you can always flip back and take a look, or to write them onto a formula sheet so you're able to keep track. I don't like this here. I'm going to erase it and scoot this over because I like things to look pretty. So that looks nice and neat now. Okay. Our last set of examples is going to have us sketch a graph of the different functions given the piecewise defined rules. So for this first one, if x is less than 2, I have absolute value of x, which looks like a V centered at 0, 0, with a slope of 1, 1. All right, so I'm going to start by drawing that. I'm going to come over here to x is, so it says x is less than 2. So here's my line at x equals 2. I'm only using this line right now as a guideline to make sure I know where to graph my function. So normally I would have a graph that goes through like this. Here we go, through this point 1, 1, 2, 2, and so on. Right, and I go the opposite way with symmetry. Now that's my graph of y equals absolute value of x. However, I only want that graph when x is less than 2. So I'm going to come over here and I'm going to erase this little bit that was greater than 2, right? And because it says that it's only less than 2, not less than or equal, I'm going to put an open circle here to indicate that on that line, x equals 2, my value of the function does not get its value from absolute value of x. On the other hand, it is going to get its value from our second part of the function, which is f of x equals 5. So here's my line, y equals 5. And starting here at 2, I'm going to graph my line going to the right of y equals 5 for all the values of x that are greater than or equal to 2. And again, I use my closed circle because it's greater than or equal to 2. Finally, well, I guess not finally, our next example says that f of x is 4 if x is less than 0. So I'll come over here. I know that my x-axis is where my 0 is. Okay, so, or my y-axis rather. So for everything less than that, x is going to be 4. Notice it's less than, not less than or equal to, so I'll use an open circle. And I'll draw an arrowhead to indicate that this goes on forever. And then for the second part of the function, I have that the square f of x is the square root of x. And the square root function is going to be when x is greater than or equal to 0. And you can remember the square root of 1 is 1, the square root of 4 is 2. And that's going to let me just get a guide for my square root function that looks like that. Okay. So it's important, again, that you know your parent functions and that square root of x has this shape. Okay. And last but not least, I have a function that's defined in 3 piecewise intervals. The first says that if x is less than or equal to -2, that's over here, if x is less than or equal to -2, the function value is 3. I'm going to put a closed circle because it's less than or equal to -2. And my arrowhead to indicate that it goes on forever in that leftward direction toward -infinity. Now, if I'm going to pop down and notice that it becomes 3 again when x is greater than 1. So I'm going to plot that on my graph with an open circle and my rightward arrow. That's my third part of my function. And then for my second part of my function, remember, I'm going to use the structure y equals mx plus b, where b is 1 and m here is -1 because I have -x plus 1. So I can use that by first plotting my starting point, which is my y-intercept. So I'm going to go over to x equals 1, or to y equals 1 on the x-axis. I'm sorry, on the y-axis, I have y equals 1. And then I'm going to go, using the slope, I go over 1, down 1 to get to another point. I can also go left 1, up 1. All right, and this is going to show me the pattern that I'm going to follow to draw my line. So just like that. All right, and I have so at the -2, the function value actually winds up being the same as the previous function. We just know that it connects to that closed-in dot that was part of my first piece of the piecewise function. Then down here, I'm going to have an open circle on 1. And I'm going to do that because the value of the function is actually 3 when x is equal to 1. It's not down here at the 1. So I have an open circle here. Nope, I have a closed circle there. Hello. And that lets me know my value of the function is actually 1 at that place, is actually 0 at that place, whereas it is 3 after that. All right. So I feel like I might have said that in a confusing way, but I hope you're following along with me and it makes sense how I'm getting this graph, where I put the open circles and where I put the closed circles. If you have questions, please don't hesitate to contact me. I'm always available via email, or if you want to make a Zoom appointment for help, I'm here. I'm also available in my office on Wednesdays and Fridays from 12:30 to 3:30, but you need to either arrive or make an appointment by 1:30, or I'll split if I don't have kids after that. So thank you and have a great night.